All right, so we'll see how this goes. Of course, Microsoft has updated PowerPoint and my whole system has changed. So this may be a train wreck, but we will try to get through it. So this next couple of videos, I want to talk about symmetry and flux and basically how we can use the idea of creating a similar symmetry to a charge distribution, which will let us make some assumptions about our electric field and actually use symmetry arguments to make this process much easier when we start thinking about electric fields and things like that. Um, this hopefully will be pretty short. It's only two videos for this particular topic. And then in this first video, we're just going to talk about symmetry flux and then calculating flux from that symmetry. Um, so the idea here is that we say a charge distribution is symmetric. See if this works. Good. If there's a group of geometric transformations that we can do on it that actually don't cause any change. So basically, if there's things we can do to it geometrically, but then we don't notice any differences. So no cause of any physical change. This basically can be summed up in a single idea, such that the symmetry of an electric field must match the symmetry of the charge distribution. Okay, so what we're equating here is the electric field and the charge distribution, though the symmetries of those two things need to be the same. The three approaches we're going to look at here are essentially translational, rotational, and reflective. These are the basic symmetries that we can consider. So the best way to think about all three of these is to just consider a really long wire, like you might have in, I don't know, maybe your car, the electrical system in your car. Basically, the idea is that if we think about a translation that's parallel to the axis, okay, well, if we look at the original cylinder, which is here, okay, and then we want to maybe we start looking here, we slide over to the right. Well, that's a translation, but and it's parallel to the axis. But what the wire looks like in the first spot here is essentially what the wire is going to look like in the second spot. There's really no difference between those two. We think about our rotation about the axis. Well, we could rotate this wire, but we may not even notice that it's been done, right? So if we were looking at it here, we rotate, that point might move as we rotate it, but unless we like make a dot or a point on this thing, we're not going to know it rotates. Um, we also have a reflection parallel or perpendicular to the axis. So the whole idea here is like you could literally mirror it, but because of its symmetry, you're not going to know that it's actually been mirrored because the before picture and the after picture are going to look the same. Now, this logic here actually will help us determine what the electric field from a charge would look like. So if we think about this first setup here, um, so the whole idea is that if we had a distribution of charges, okay, so the first thing we're dealing with symmetry is the distribution of charges. The second thing will be the electric field. So if we have a distribution of charges this way, well, if we reflect it across this axis here, the charges will be the same. But if we think about this hypothetical electric field, so you can see how we're just sort of assuming here that, well, maybe it's, the electric field's on an angle. We know it's not, but let's just assume that. So the idea here is that if we can reflect across this axis and the distribution stays the same, then that means whatever the electric field is, it should stay the same as well. So you'll notice if we do reflect it, all of a sudden our electric field points in a different direction. Different direction. I'll abbreviate that with just dir. However, the charge distribution stays the same. So this will actually be the same. So the idea is that same charge distribution, but the geometry of the electric field changes. Okay, we can do the same thing if we think about the electric field, same wire, but we have the distribution, we're looking head on at it. So the idea is that, well, maybe the electric field comes off of this as a pinwheel. But if that were the case, if we were to reflect it across a vertical axis, well, then that wouldn't change the charge distribution. You can see here, the charge distribution stays the same. We can't tell that the distribution flips, but we can tell that the electric field has now been reflected and pointing in a different direction. Okay, so far, this doesn't make any sense because it doesn't match the charge distribution. This one doesn't make any sense. The only one that makes sense, it's notated right here, the only shape for an electric field that matches the symmetry of charge distribution in a wire is if the electric field is actually perpendicular to that distribution. So you can see here, we have one string of charge distribution, and then the electric field is essentially perpendicular. So that'd be your right angle. Now, if we were to reflect this, everything would be the same. The charge distribution would be the same, and the magnitude and direction of the electric field pointing vertical up and down. That would also be preserved. Same thing here. This is actually going to be the same on either side. If we reflect uh, from like an end view, if we reflect off that line of that axis. Okay, so just using these simple assumptions alone, the shape of an electric field can actually be determined. Just like we did, we showed without doing any crazy math that the electric field from a wire should actually have the same symmetries as the distribution. But this doesn't tell us anything about the strength of the electric field. Um, this is more helpful to just rule out electric fields that are not possible. It's not necessarily the best way to give us information about what this field might actually look like. Okay, so it's a bit limited in what it can actually help us do. But there are three fundamental symmetries that appear in electrostatics. So we have the symmetry of a plane. You can see this sort of passes the sniff test, so to speak, of the symmetry arguments that we've looked at, where you could translate, you can reflect, you can rotate, and everything pretty much still lines up. You could, I guess, technically take the plane and rotate it up from this way to this way. But even if you did that, your electric field would also rotate. So it's not like you're rotating within the electric field. So this one still passes that um, test. The cylinder we've already done in the previous slide pretty much. We know this charge distribution in this electric field passes the test. And then another important one is this spherical symmetry. Basically, if you think about a ball and it maybe is enclosing a charge, well, the charge, if it's a positive charge, is going to have electric field pointing out everywhere. And then that's always going to be perpendicular. Okay, so we'll have lots of right angles. It's always going to be perpendicular to the surface. So no matter which way you turn that ball, you're always going to have perpendicular fields. And a way to think about this in more practical examples is essentially for the planar symmetry, that's going to be like a parallel plate capacitor, which we'll talk more about later. There's also like coax wire where you have your positive inside and your negative outside. You all may be too young to remember coax wire, but that used to be how you would connect like cable TV. That's how you connect it to the cable itself. Um, and then we have concentric spheres. So this is basically sphere with some sort of charge inside another sphere of charge. Okay, this is three different examples where the symmetry would show up and be important. Now, let's start applying this in terms of fluxes and Gaussian surfaces. So suppose we have a region of space and it's surrounded by a closed surface. So if this is our region in space, okay, maybe it's a little square parcel, and then it's enclosed by an entire surface, okay? So we have a clear inside and we have a clear outside. All right, so this closed surface is actually going to be called a Gaussian surface. Um, this is basically just an imaginary mathematical surface. Okay, so Gaussian surfaces aren't real things that you can touch. It's a mathematical idea that you can put around a real scenario. So we could have like a cubic Gaussian surface, as you can see here. We could have a cylindrical Gaussian surface. The idea here is essentially if you were to enclose an electric field, so there could be like a positive particle in here, you can enclose that in a Gaussian surface, and ideally, all of your electric field lines coming out, they would be perpendicular to the surface itself. So clearly, cube wouldn't be the best fit for a single charged particle because we would still have uh, E fields, electric fields on the diagonal or like diagonal values. But you can imagine if we had a wire like we've been talking about in here, we had a wire that would fit very well with a cylindrical Gaussian surface because we could fully encapsulate it. All of the electric fields coming out would be perpendicular to that Gaussian surface. That's the main idea here. The better fit for a charged particle instead of like a cube would actually be a sphere because no matter what angle your electric field's coming out at, um, ooh, that's a bad E. There we go. You're always going to have those perpendicular angles. Um, so that whole idea is just making sure your Gaussian surface matches the symmetry of the charge distribution. In this case here, it's just a single charge, so that's easy to match. A Gaussian surface that doesn't match the symmetry of some sort of distribution, that's not very helpful at all, right? You can't really do much with that. Um, Also, some sort of non-closed surface does not actually help either. So you want to make sure you can completely enclose your charge distribution that you're looking at. But from these ideas, we can actually conclude that the electric field flows out of a closed surface, um, which we sort of showed. So the electric field flows out of a Gaussian surface if that Gaussian surface is around a positive charge. You could have a mix of positive and negative, but if there's more protons than electrons, then it's going to have a net positive charge. Uh, the electric field is going to flow out. If you have more electrons than protons and it's a more negative charge, then the electric field is going to flow into the surface. Okay, that's going to be surrounding a negative charge. So the electric field may flow through a surface when no charge is enclosed, but that net flow is zero. So the whole idea here is that we have a charge here, maybe it's a positive charge, and then this is our Gaussian cube here. Well, let's see if I can zoom in without breaking everything. Yeah. Okay. So in this situation, the amount of the electric field going in is going to be the same as the amount going out. So this is the electric field from the charge flowing into the cube. This is the electric field flowing out, and these are actually equal. So the net flow in this situation would be zero. And then this is sort of what we've been talking about quite a bit. Just the whole idea that the electric field pattern through the surface is best if you can actually match the symmetry of the charge distribution inside. Okay, so here's just some pictorial representation. So this is not a Gaussian surface, it's not closed, so that's not particularly helpful. Here's an example of where the surface just doesn't match the symmetry of the field inside. You can see that these electric fields lines all have different lengths, so that's not particularly helpful either. And this whole idea of the electric flow through a surface actually comes from the Latin word for flux, or the Latin word for flow, which is flux. And basically, this is just the amount of the electric field passing through a surface. Okay, that's the idea of electric flux. It's just how much of this electric field is going through these surfaces that we defined. Um, Okay, and then again, I've listed these three ideas about outward flux going through a surface from a positive charge, and inward flux going through a closed surface if there's a negative charge inside. And then if you have a charge outside of your surface that you defined, well, then um, there's no flux, there's no net flux when there's no net charge inside. Now we can actually write this fairly mathematically. Um, the whole idea here is that essentially the flux by a non-uniform field. So here the whole idea is essentially E changes depending on where you're looking at it. So it's a non-uniform field, and it's going to be through a curved surface. We can actually describe this with a surface integral. Now we have to think about the normal vector, okay? So this is the normal vector n. It's a unit vector, which is why it has a hat. Okay, so it's got a length 1. And it is normal to the surface. And that just means it's perpendicular. So I'm going to abbreviate that perp. And we can leave this symbol here for perpendicular. Um, so it's basically normal to the surface of area A. Okay, so here, looking at the picture, this is my surface of area A. Um, and then there's going to be some sort of angle between this surface, this unit vector, and the actual electric field. So you can see here, this is our electric field. Here's theta. And then this is our normal vector. It's normal to the area. Okay, now the idea here is that we're only curious in the component that actually passes through the surface. Okay, so we only want to know about the component that's perpendicular to the surface. And we can actually get that by essentially taking the cosine of E. Um, right, so that's going to be, the cosine is going to give us this piece here. Let me see if I can try and label this in a different color. Ooh, it looks like I may not be able to. All right, that's fine. We can just leave it in red. Okay, so basically the electric flux is defined as that perpendicular component multiplied by the area. And we can get that perpendicular component by including a cosine of that angle. Okay. So basically what's going on here is the electric flux, right? So our phi, it measures the amount of electric field. So we're talking about amounts now. The amount of the electric field passing through a surface of area A, okay? And this, of course, will account for if it's not a head-on pass-through where it's like perpendicular, but if your surface is sort of turned a bit. And that's what that angle is for. So what you should notice is that this right here looks like a dot product. Remember the whole like some vector dotted with another vector is just the magnitudes times cosine theta. Well, that's the whole idea here. Is essentially if we start thinking about the area as a vector, so area is a scalar value, it just tells you how much surface you have. But if we multiply that by the normal vector, right, which is a unit vector, so length of one, we've essentially turned the area into a vector. And you can see that here. We have an area that we actually essentially vectorize. And of course, it'll always be perpendicular to the surface. Okay, so now when we start thinking about electric flux, we can just take the dot product of these two vectors, the electric field and the area vector. So we have electric field, and then we have the area vector, and then we take the dot product, which will be a cosine of this angle in between. So here, okay, you'll remember that this is essentially like a projection of one vector onto the other. Um, so the dot product is a projection. So basically, we're taking this weird angle of our surface and we're sort of projecting it. If we project it onto the electric field or vice versa, we're sort of collapsing this angle and just taking that one component to let us know how much electric field or the amount of electric field is going through this surface. Okay. Well, we can also think about this in terms of an integral because if we have a lot of these and we can add them all up, um, this is really helpful if we have a non-uniform E field. So if it is changing over some space, and you can see here the direction, at least in this example, is changing, so it's turning. The idea is that, well, we could just take small calculations um, and then add up all these small calculations over the space. And this is the whole idea of a surface integral. Okay, so this is just the really small individual components added up over the entire surface. So add, how can I say this? We'll add small calculations. Calculations over the surface. And that's essentially the idea of a surface integral. You're limiting your integral by the actual dimensions of the surface you want to integrate over. All right, so let's see if we can sort of put these pieces together. Uh, so if the E field is everywhere tangent or parallel to the curved surface, so you can see here we have our area vector. It's going to come out this way, which means we have a perfect right angle. Uh, well, if that's the case, then we know that our dot product is going to be zero, because this would be EA cosine theta, EA, well, cosine of 90 degrees is just zero. Okay, and then going about this the other way, that's one extreme example. If the uh, electric field is parallel to the surface, if the electric field is perpendicular to the surface, and it has the same magnitude everywhere, so a nice uniform distribution, well, then our surface integral is going to uh, become really easy, right? Because if E is not changing as a constant, we can pull that E out front, and then all we have to do is just add up pieces of the area, right? So if we have a surface integral and we add up all those little pieces, that's just the total area. So in this situation where everything is perpendicular to the surface, so we have all right angles, we get the most simple calculation that's not just zero. Full magnitude of the electric field times just the total area. Okay, now we've talked about this just over some surface, but we've also talked about Gaussian surfaces. So we need to come up with a way to write this flux through a closed surface. And that's what this circle means here. So this is the flux through a closed surface. So this is the nice like sort of Gaussian rule that we're looking at here. You want to take your dot product, but you want to examine that dot product over a closed surface, and that's what this surface integral here is indicating. Okay, so with that, that's sort of the conceptual idea behind Gauss's law and the whole idea of like flux through closed surfaces. So next time we'll actually talk about using this calculation and looking at some examples a little bit more in depth.